All set?
Yeah.
Thank you. I'll be talking about glaciers, climate change, and the effects that glaciers melting have downstream. And since we're filming this, I know you all know where we are. For the film, I'm going to say we're at Mount Rainier National Park, and it's in the Pacific Northwest, about halfway between Seattle and Portland. And what I'm going to talk about today is to show the very real effects of climate change on Mount Rainier's glaciers and the impacts that they're having on both the park and downstream communities. And I encourage questions as I go along, and this is my first time presenting with a mask, so if you can't hear me, definitely let me know, please. And I won't be using my ranger voice, but maybe my meadow rover voice, which I'm told has to be very nice. So, more specifically, what I'm going to be talking about today is the importance of Mount Rainier's glaciers and climate change and how it's affecting those glaciers. And then I'm going to look at ongoing glacier research and some emerging geohazards from these glaciers and the effects it's having both downstream and regionally below the park. And we can definitely see glaciers from here. A little side note, I'm going to also be doing some safety notes as we go on the side. And these glacier dancers from this historic photograph are a little too close to the edge. But basically the reason she can see glaciers from her house is that Rainier's glaciers are among the most visible in the whole world, or certainly in North America. Being right near both Tacoma and Seattle. And not only is it its proximity, but there's a lot of snow and ice there. There's 25 named glaciers, there's over 35 square miles of glacier ice, and there's a cubic mile of ice. If you added it all together, it would be like a block by 1 mile, by 1 mile, by 1 mile. And it's perched like a mile or two above sea level, so there's a huge amount of energy there. And we could fill T-Mobile Park a lot more than the Mariners fans could. In fact, there's more snow and ice than all the other Cascade volcanoes combined. And it's the largest sort of glaciated massif in the contiguous part of North America. And the reason I know this is early on in my career, when I went to grad school in the early 80s, I was part of a project to measure the ice on the Cascade volcanoes. And this was all motivated by Mount St. Helens. Those of you who have been around here as long as I have, you might remember St. Helens when it looked kind of like Mount Fuji in Japan. Well, it started advertising that it was having some problems beginning the spring of 1980. First there were some little steam eruptions. That was followed by some ash eruptions. And finally, we had the big major eruption, May 18th, 1980. And because of the damage caused by that, the USGS decided to measure the amount of ice on all the other Cascade volcanoes because the floods were mainly bulked up by all the melting snow and ice that was on St. Helens. And St. Helens is one of the smallest volcanoes, with the smallest amount of ice. So their idea was to do that. And I became involved as a grad student with that project with Carolyn Dreger at the USGS. And we used a backpack, it's called a monopulse radar. It's just like puts out a packet of radio waves that went through the ice, bounced off the bedrock, and came back. And that time that elapsed between sending it and getting it back, you can calculate the thickness of the ice. So we had a backpack unit that did that. And this is my second safety note, though. If you notice, like above my head, there's like a line. That's a crevasse forming under the snow. So we basically parked the helicopter and myself on a covered crevasse, which is poor form glaciologically. And we ultimately ended up publishing the data, Carolyn and I, with all the stats so that the hazard could be calculated for the volcanoes if they were to erupt, how much it would bulk up the flooding. And like I said, there's enough ice actually to fill a line of dump trucks, bumper to bumper, 23 to the moon, 23 times a day. So there's really, even with climate change, there's quite a bit of ice up there. And then the Mount Rainier's glaciers, they are real glaciers. Now those of you who rove, and maybe all of you know where Glacier Vista is in Paradise, if you were to look down on the ice there across the glacier, that area where the arrow is, it's been measured to be 400 feet thick there, the ice. So the Nisqually still has a lot of ice in it. And the carbon had the largest measured depth of 705 feet. So it's quite deep too. And the crater itself had 250 feet measured. I stole these slides from Carolyn Dreger, who some of you know, and she's with the USGS, and she does outreach and education now, but she was a glaciologist back in the day. And so I'm going to do a little Glacier 101, because I've been accused of doing these glacier presentations without talking about glaciers, because I end up talking about floods. So, but basically what a glacier is, it's a perennial body of snow and ice that is so large and heavy and thick that it can flow under its own weight, by gravity, in a very slow way. It's like if you left silly putty out overnight as a ball, it might flatten on one side overnight. Very slow. And the way it works is that the upper part of the glacier, you essentially get more snow every winter than melts in the summer. And the lower part of the glacier, called the ablation zone, gets snow too, but it has more melt than actually snow falls. And the only reason there's snow there is because the glacier is thick enough to flow. And so it's being replenished from upstream, and that's why you can have more melt at the bottom. So that's one thing you just have to keep in mind, that glaciers move, and that's important for this talk. The other thing just to know is that snow metamorphoses or transforms from crystals, very complex snow crystals, down to ice, and it does it relatively quickly here. It's on the order of like a half dozen years. If you go to some of the really cold glaciers, it can take up to centuries. Yes?
Yeah, Paul, do we know what the average firm limit is on Nisqually by chance?
It's probably rising. They do know that. I'll get into this project called Glacier Mass Balance, and they would know. But you're right, the equilibrium line, which is sort of where the firm limit is the area that marks between the accumulation and the ablation zones shown there. And I'm sure it's been going up, though, because the glacier is shrinking. Okay, so that's kind of how glaciers work. But there's some functions that they perform, some of them good, some of them less good. A real advantage to having a glacier being the source of your river, like the Nisqually is for Tacoma, for example, who uses the water for power, is that during a drought year like this, instead of the river drying up, it actually gets more and more water. So it's great for summer flows and to also keep the temperatures low for fish. Also, glaciers are excellent indicators of climate change. And also, though, they have some geologic hazards associated with them, which are the more negative parts of having a glacier around. And we've all heard climate change, especially after this summer. I imagine that almost everyone's becoming more of a believer. And I'm not going to go all Al Gore, but I just want to mention that climate change is happening. It's caused by people, and the Earth is warmer than it's been for quite a while, and it's affecting our glaciers. And glaciers magnify climate change because they're really sensitive both to temperature changes and to precipitation changes. Now, I was talking about how the snow turned to ice, and this actually kind of shows it. This really white snow is like last year's snow. So if you came out in spring, the whole glacier would be covered with this. And when it melts away, it exposes the year before snow. And it's a little dirtier because all the dust that accumulated on the first year, when it melts, it goes to the surface, stays on the surface, it goes on the next one. And the dirtier one is just a year older than that. And then eventually, after like about 6 or 7 years, something like that, it turns into ice. Now this is the view, if you were standing under the Nisqually Bridge that crosses the Nisqually River just up from where we are today, and looked up, and it was the turn of the century, 1900, you'd have that bulbous ice from the Nisqually Glacier. The terminus would have been right there at the turn of the century, 1900. And the building in the lower left was actually an ice cream stand that was there, and they used to use the ice to make ice cream to sell to the tourists going up to Longmire. Now, back in the 1600s, 1700s, and 1800s, it was colder for a variety of reasons than it is now, and it's called the Little Ice Age. And because glaciers respond to more snow and colder temperatures, the Nisqually was much further than it is now. It extended in 1840, the furthest it went recently, to below where the bridge is now. So if you stood up on the Squally Bridge and looked downstream, you'll see an island of trees not that far down below the bridge. That's what they call the terminal moraine, or basically a pile of dirt the glacier put there in 1840, the furthest it went. Since then, it's just been retreating. Now when glaciers retreat, they don't flow uphill. They keep flowing forward. They just melt faster, so they melt uphill. But it's like the tide going out. Since 1840, it's been bad for the Nisqually. Going further and further up. But during the late 50s and 60s, it started snowing a little more. Natural variation of climate, and a little more snow and a little cooler, and it actually advanced. So it's like the tide going out, but a wave came in, and the wave, actually a couple waves came in, but the tide kept going out. And now the glacier is off that picture. It's so far melted up, it's not even on that picture. It's like 1.5 miles at least from where it was in 1840. This is in the Nisqually. But we're sort of fortunate that Nisqually has one of the longest records and more complete glacier research in the whole Western Hemisphere. And they actually started in the mid-1800s. And the USGS began its research in 1896, and they've been measuring with the terminus ever since 1918. And I do want to point out the last bullet is that, especially the Beeson article, so there's some maps, some relatively recent maps of the glaciers, but Scott Beeson, who's a park geologist, has a park publication on the glaciers that's kind of the Bible. It says the amount that there are, and the ones that have disappeared, and the ones we still have. And I guess it'll stay the Bible until we lose another glacier. And there's a lot of glacier research. Now, this was the glacier research that was going on when I left. I haven't updated it, but essentially it's going on. We don't need to go into the details. But I am going to be talking about the ones that are in yellow, and so you don't have to really read anything now. But most of this research is continuing under Scott and his crew, and other people. And North Cascades actually does the first one. And I think probably the most important project is the mass balance, it's glacier mass balance. Now, if you look closely, this is the middle of the Emmons Glacier. If you look closely at the surface, you just sort of see water running everywhere. The Emmons is really melting quite quickly. And what glacier mass balance is, it's like a big checking account. The snow that comes in is like a salary for your, the money you put into your checking account. The ice that melts is like your spending, and your checking balance or the glacier, reflects that. If you're getting more money in, then the bank account is happy and your glacier's happy. More snow in, glacier happy. And they did some research, and they finally concluded that they could measure where the stars are just on the Emmons Glacier and then the Nisqually Glacier, and then extrapolate that information around the rest of the mountain. Now, essentially what they're doing, there's really two sets of measurements, and it isn't really just one visit, but in the spring, they go out and they measure the snow, how much snow fell, so all the white. And they have to actually, because snow can be either heavy or light, they have to figure out the density and sort of convert it to water. So they figure that out, and then they also use a steam drill that they have to carry up there. And make holes in the glacier to put some melt stakes in. And they have to go really deep, because we get a lot of melt. And so in the fall, they go out and see how much snow is left. And you can see a lot of it melted compared to up there. And then they measure how much ice, how exposed these stakes are. So that's where you're really going into the principal in your bank account there, and how much really melted there. So they have spring measurements and fall measurements. And I just want to give you a sense of what the Nisqually Glacier looks like in the spring. It's like a beautiful Christmas card. And in the fall, it's not so beautiful. And I've had volunteers where we've had projects out on the glacier. It's very easy to get people in the spring. And when you're stumbling around, it looks like a little rock there. These are boulders, and there's crevasses, and it's kind of a mess. It's really, you have only your most hardy volunteers in the fall, but we had some that stuck through the whole project, which is really great. Anyway, this is kind of what it looks like. The spring visit, if you have good weather, it's really hard to schedule the spring visit, how springs are around here. But you go in and you actually dig pits to see how much snow there is, and then you melt it to see how much water equivalent there is. And then you start drilling. And the drilling just goes on like forever because you have to get like 10 meters deep. And the steam drill just has a hard time keeping its steam that deep. So that's what it looks like in the spring. And then in the fall, you go and you measure how much snow is there, but mainly you're measuring how much ice melted. And it's kind of amazing, even if you're having a good year, a normal year in the Nisqually, sort of pre-climate change, you're still losing 10 meters, over 10 meters of ice at the bottom of the Nisqually, because it gets so much sun. You can kind of believe that, how hot it is. And on the Emmons, the other side of the mountain, where it's a little, it's less sunny, you get a lot of melt too, but not quite as much. But we keep losing our glacier monitoring people there. So this is the data.
You mean 10 meters of length or depth?
So you get 10 meters of ice actually melts of depth. And that's all replaced, remember, theoretically by the stuff that's flowing down. Except, well, in this case we'll see that, well, we know it already retreats, so it's not quite replaced. And this is what the data looks like. The blue is the amount of snow. So they started in 2003, and I've got the data actually, this is the most recent data. They were very kind to supply that. The blue is like how much snow came each year. The red is how much melted each year. And then if you subtract the two, that's the purple. So it's the difference between how much came in and how much went out. And if it's below zero, that's bad. You're spending too much. You're deficit spending on your glacier. And the Nisqually, we can see here, 6 of the 18 years were positive and the rest were negative. And even some of the positive ones were awfully small, as you see over there. And on the Emmons, same thing in the Emmons, except it's even worse. Only 3 of the 18 years were positive. So the Emmons is taking a bigger hit. And this just shows them together. And you can just overall see it's more below zero than above. So that's not good. And then we added up all the numbers together. And the blue is the Emmons, and the red is the Nisqually. Now the Nisqually was losing a lot of stuff. This is how much water equivalent in meters that it lost. And losing 7 meters represents a huge amount of water, like almost 40 million gallons. But the Nisqually was losing quite a bit and seems to have kind of rallied and stabilized. Now they just started calculating the data differently this year. So they're not as certain that that data is great, so this may not be quite as stable as it seems. It may be a little more negative. They'll know that better in a year or two. But the Emmons, they are doing the same way, and it's having a very hard time. It's lost over 14 meters of ice since 2003. And unfortunately, this 1962 advertisement proved prophetic. And I'm sort of, as a volunteer, not since I don't work for the park anymore, I can be a little bit political, but anyway, part of it's obviously caused by our burning of hydrocarbons. Now, just to make it so you can sort of understand, everyone's kind of familiar with the Muir snowfield. Here it just shows a Muir snowfield that's pretty much devoid of any new snow on it. And if you look closely, you can see several years of old snow melting there too. And they've been losing at least a meter of ice every year since 2003. Now the Muir snowfield starts at 10,000 feet. It's not that high, so it's really taking hits much harder than one like the Nisqually starts way up at the summit. And even in the worst climate change, you're not going to lose all your ice at the summit. Though you might lose a huge amount at the bottom. Anyway, so it's the glaciers that start in the middle of the mountain, the highest parts in the middle, are most vulnerable to be losing them. And again on the Muir, they're actually getting bedrock showing just recently for the first time ever in places they've never seen it. Almost every year they have crevasses opening up. Most people when they go up the Muir snowfield don't use ropes, but they're getting crevasses opening up there now earlier and earlier. So the famed sort of climber's gateway is getting a little ragged. And overall, just to really bring the point home, is they've lost a huge amount of ice. There was a student, Thomas Nyland, got his PhD at Portland State, and he, for his doctorate, estimated the amount of ice loss between 1913 and 1994. They lost about a quarter of the ice. And this hasn't been updated, but since then they've lost about 20% of the ice. And that rate, though, this is the take-home message, is that the rate of loss is 100% higher than it was earlier. So it's like the ping pong ball fell off the table on the graph and we're losing ice more quickly. And while there is an enormous amount of ice at Rainier, we have lost glaciers. And we listed the glaciers that have lost during my lifetime on the left. And that paper I mentioned of Scott's from 2017 has sort of definitive ones of the ones we've lost. But the most iconic was the Lower Paradise Glacier, which had the Paradise Ice Caves. Is anyone here old enough to have been in the Paradise Ice Caves? Anyway, you knew how it was visited by up to 1 million people in its heyday. Yes?
Wasn't the last remnants of the caves 1992? I can't pin a date.
It was right in that area. They closed it, I believe, in the 80s because a chunk fell down and hit one of the people in it. And the guides used to bring people from Paradise there. They used to have 1 million visitors. And they had up to 8 miles in the network of tunnels in its heyday. This is like 70s.
Yeah, I just remember, I keep thinking back and trying to think, God, was it 92 that I saw the last, shell with an ice cave of some sort up there? I think it was.
It was very close to that if it wasn't that. And there used to be a sign. In fact, I found that sign years later, but then it disappeared that year. Someone took it. Did you have a question?
Are ice caves human-made or are they naturally occurring glaciers?
Oh, they're naturally occurring. And what happens is, and we'll get to this later a little bit, but the glacier's in such bad shape, the ice doesn't move anymore at the bottom. And there's water actually flowing out of this cave lower right, and it entrains air behind it, and it just makes this big cave. And since the glacier is not moving, if the glacier were moving, it would squish that cave. So it allows the caves to flower. And it's sort of this beautiful last moment of a glacier that's basically dying. Now, one silver lining, I'll probably screw up the archaeology here. One silver lining is Ben Diaz, who's a park archaeologist. I worked with him to create a predictive model of what ice patches would most likely have prehistoric remains in them if there were remains in them. And the idea is that to go and map those, and then on low snow years, big melt, is go look in those identified ice patches for archaeological or sort of, previous human use artifacts or paleobiological material melting out of the ice. And they haven't found much on their initial surveys, but in the meantime, while we're waiting for the final, is a lot of things. Keep your eyes open whenever you're around an ice patch late in the year. There's stuff melting out. There's a doughboy hat that came out on the Muir snowfield since was here. And if you walk on the Nisqually or below it, and if you go below the Nisqually up above the bridge, it's very dangerous. You really have to watch out for rockfall, so know what you're doing to do that. But if you go there, there's lots of airplane parts. And that's because planes crashed into the upper Nisqually, and then since then the glacier ice has moved them down and is spitting them out. And actually, from below Glacier Vista down on the ice, you can pretty much find airplane parts. You can almost be guaranteed, like this time of year, to find pieces of metal and other things. Okay, the second project I want to talk about started in 1930, so it's probably one of the longest running glacier projects, at least in North America. It's called the Nisqually Survey, and there's 3 profiles. This middle profile is about at the middle of the glacier, and you can kind of see where it is over there. And then, so there's 3 profiles starting in the middle of the glacier and then going down near the bottom. And since they've started, in 2014, the glacier had retreated so far, it took out the last profile, so they moved it. Then in 2015, it took it out again, and I talked to the people who are doing the project now, and they don't even bother with the third one, so they're only doing profile C and B right now. And what they do is they go out in the fall, when there's before the new snow, so it's the smallest the glacier's going to get. All the summer stuff is melted right before the next first snowstorm. They go and they measure. They go across the profiles, and they actually have survey rods, and there's a surveyor who takes a shot. And they can get the exact height, how high those profiles are each year. So they just used traditional, or then they used traditional, they just switched to GPS last year. But anyway, the interesting thing happened is that they discovered that one year they went out and suddenly profile C was 10 meters or 30 feet higher than it was the year before. The whole profile was 30 feet higher, and they go, that's weird. The next year it dropped down to normal. And then a couple years later, profile B did the same thing, it went up. A couple years later it dropped down. And then a couple years later, A did that. And they realized something was going down the glacier. And it's almost like a snake eating a mouse. You can kind of see the bulge going through. And what they're getting is a kinematic wave. So there's some years where you actually get really good snow accumulation, more than normal. And it actually makes this steepening front at the top of the mountain, sort of a bulge. And gravity forces a wave down there. Now your ice is kind of moving at a couple feet a day, normally. This wave moves 4 or 5 times faster. So this bulge on top of this glacier moving slowly just moves even faster. And that's what's making when it hits the profile, when it hits C, it goes up, down, and it hits B, up, down. So it goes through, and then what happens is when it hits the terminus, it usually advances the terminus. And this is a little hard to see, but if you look at it really carefully, you can actually see 4 waves. You have to look at it that way, where it goes higher here, then higher here, and higher here. 4 waves, and when they hit the terminus, 3 of them advanced the terminus, but the last one, in the 2000s, it hit the terminus went faster, but it melted even faster, so it retreated. And these are some pictures that, some old pictures that show sort of this phenomenon. So this was taken in 1944. And does everyone know where the Nunatak is on the lower glacier? It's that kind of isolated mountain you can see from the Squally Vista down there. This is the Nunatak, and the glacier now is above that. The lower part of the glacier is up like where the 1944 is. But back in the 50s, or 40s, I mean, it was next to the Nunatak, and actually it retreated. By 52, it went back a little bit, and then look at the glacier ice on the left, and it's advanced by the end of the 50s, and then in the 60s it overrode the Nunatak, and that's when that kinematic wave hit the bottom. So this just shows the maximum extent after that kinematic wave hit. So we know there's lots of melting glaciers, and the problem is that these glaciers are not going quietly into the night. They're causing some problems as they disappear. So I'm going to be getting into that part. Earlier I showed some of the glacier functions, and now we're down to the geologic hazards, the outburst floods and debris flows, and the problems those cause for flooding in and outside the park. I might run this twice. So just look at, since 1913, glaciers have been retreating like it shows on the Squally. And the problem is they expose just a huge amount of really loose sediment. And they're doing it sort of in 2 different places. When they pull back like on a higher upper flat slope, they're just exposing just a bunch of very loose stuff on a very steep slope. And whenever you get your like fall range or atmospheric rivers, your Pineapple Expresses, it's very easy to move that stuff down into a river. And then this big pile of dirt, which I'm sure you've seen like from Glacier Vista or from the Squally Vista, is a moraine or the deposit that was put there when the glacier was in the little ice age I was talking about, when it was down in 1840 below the bridge. The ice was actually this high in 1840. But it wasn't falling all into the river because the ice was kind of holding it up, it was bracing it. And then as soon as the ice melts back, this stuff just, you look at it cross-eyed and it starts to crumble into the thing, into the river. And this is just a picture of just showing locally, this stuff falls into the river, it gets in the river and starts moving down. And for you people on Sunrise side, this is the Emmons and the birth of the White River, really. And there's so much sediment up here, the river can't even process it hardly. But eventually it does, and it starts moving the stuff down. And they're having lots of problems on the White River, too. And this is a cartoon. So when you get just like, it doesn't have to be a flood, it can just be a big enough flow where it's moving material, like when you hear the rocks banging sometimes in the Nisqually. And then when that flow sort of settles down and goes back to normal, it drops all the rock it has and deposits some. Then the next flow goes in the low spot, does the same thing, but it's building up the bed as you go. And eventually that bed gets high enough, you literally fill the bathtub with rock, you fill your river with rock. And a regular, just a small, doesn't even have to be a flood, starts hitting your house or your buildings next to the river. And the result is aggradation, or just lots of sediment. And you can see the trees on the left have died. They've been buried and they're literally suffocated by all the sediment. And this is that lower Van Trump curve where the Van Trump, it's where you're driving up and it looks like, why did they build the road here? So here's our first and only quiz. Our rivers are filling up with dirt. What is the recent rate of aggradation? Is it an inch per century? Is it an inch a year? An inch a decade? Or is it over a foot a decade? Does anyone have a sense?
D.
Say B?
D.
D. You're all ringers. Well, the historic rate was less than 3 inches a decade, which is actually quite high. We found an old stump that was a couple hundred years old, and we carbon dated it, so it was buried. So that's how we knew. But you're right, the current rate is over a foot a decade. Some places it's 3 feet a decade. In any case, it's well over its historic rate. So glaciers are melting faster, rivers are filling up faster. Because I love standing under the Nisqually Bridge. Here we are again, and this is the ice the way it looked in 1903, I'm sorry. So the glacier was right there. They didn't have the bridge then, they had the little road down, and you can actually see the old road abutments if you look off the bridge. Anyway, by 1942, the glacier had gone all the way up here. Oh, that's our Nunatak, incidentally, that I mentioned earlier, in case you didn't know where it is. Nunatak is actually an Icelandic word for a mountain surrounded by ice, so it's our former Nunatak. Now I want you to look at the dirt or the river bottom right at the bottom there. Just see what happens by 2012. That has aggraded or risen by 5 meters, which is over 10 feet. So since the 40s, the river right under, just by these photographs, has risen by over 10 feet just since the 40s. And that just gives you a sense of what all our rivers are doing. And this is the White River, so for people on the other side of the mountain. And this is the State Route 410. Crystal Mountain is down at the end of that, about a mile away. And if you went into the woods a couple hundred yards, you'd find the White River. And the bed of the White River is it's been measured, full 16 feet above this road. So it's actually what they call a perched river. The bed of the river is 16 feet above the road, and the only thing holding it in is the old growth. Well, a little flood channel escaped, and there's a wall built here now. This is when it first happened. There's a little wall you drive by now. But anyway, often that river is higher than the road, even in the summer. Before, someone could just go by someone with bad intent could just go by with a shovel and release that river. And now every time it rains, we get a little bit of, we get a flood on the 410. Yes.
Yeah, I heard somewhere, I don't know from who or what, doesn't matter, that the museum might be 200 feet lower than what the surface of the aggregation of the river is.
Oh, I don't think it's 200, but yeah, you can just go down there and look up.
Yeah.
So you mean in Longmire?
Yeah.
Yeah, you can just go down to across the museum and look up and see it. But there is a visual that has it. I just can't remember off the top of my head.
It probably meant over history or something like that.
But Scott Beeson's project showed that because he was measuring all the beds of the rivers, the aggradation. He's a park geologist. Anyway, this is a tremendous vulnerability of 410. I kept thinking it was going to take 410 out, and it hasn't, but I think its time is still limited. All right, so our rivers are filling up, but it's worse. We're getting bigger. Not only is the rivers full and can't hold as much water, we're getting bigger, more frequent floods. If you look at the stream gauge for Nisqually, what used to be a 100-year event you use the more modern data, is now occurring every 14 years. So you're getting the old 100-year event every 14 years now in the Nisqually. So we're getting bigger floods, and you're getting that to a degree on many of the other rivers, not quite that bad. So with the climate forced increasing river flows and decreasing transport capacity, we've essentially been having some significant flood problems since 2003. And we've had the usual road failures. These are on steeper slopes, and if your river or stream is at right angles to the road, it's bad for the road when it takes it out. But it's kind of a limited distance. It only takes out a relatively small area. What's even worse is like the Carbon River Road, which is closed from flooding, where the roads run parallel to the rivers. Now roads, if you look at it, are much smoother than the forests. So if a river water, a flood water gets on the road, it likes it because it's much easier to flow down. So it's almost a magnet for when water gets on it. And it wants to flow down the road. Because of that, you can get potentially miles of damage that way. So it's worse to have a road right next to your river. And I don't know how many people remember this, because it sort of happened during COVID times, but it was like a really bad winter in 2020. We had about a foot of rain, and every single park entrance was blocked, including a debris flow. It was sort of near Copper Creek, but it was out here, that blocked the way you probably came in on State Route 706. And that's a picture of State Route 706 lower right. And the Nisqually entrance remained blocked for quite a while. That's a lot of junk. And there were 200 residents up in Nisqually Park who were basically stuck. They did start running a shuttle. They plowed into the back gate and then started getting some. They could go out once a day and buy whatever they bought. But anyway, closed the park until the end of February. So that's just the kind of problem we're moving into more and more frequently now. So we're basically having some real challenges to access because of increased flooding. The West Side Road has been closed since the 80s when they started having a ton of debris flows. And that used to be a huge recreation. I mean, a lot of people went up there even then, like over 50,000 people a year. And anyone who's been up there, there's just tremendous hiking. It's kind of hard to get to. You have to bike or walk to get to it. And the Carbon River closed in 2006, and while the park is still a little bit optimistic, I can almost guarantee it's not going to open in its current location. The Road to Paradise is at the highest risk, though it hasn't failed yet. And Sunshine Campground, our only year-round campground, gone in 2006. So we have no year-round campground. And the White River I talked about earlier, it's at very high risk. And this is reducing our non-hiking access. You're unable to actually maintain cultural resources. The West Side Road is the highest level of historic significance, but they can't maintain it. The rock walls are falling apart just because they can't get material up there easily. Or it was that way. So anyway, these are some of the problems you get. So what's happening overall is that rockfall is driving everything. So all these I'm sure the rovers hear rockfall all the time, especially this time of year. Well, all that rock goes onto the glaciers. The glaciers, remember, move, and they move all that rock eventually and dump it into the rivers. And then it causes a huge amount of problems for a variety of reasons. There's debris flows, and floods, and other mechanisms bring it downstream. So rockfall is sort of the main thing. And this is actually a rockfall that happened in 2011. And this is sort of the middle of the glacier. There was one of the guided groups was going to go across this way, their way up to, I guess, the Couch group. But anyway, it was a big rockfall, but it's considered really small compared to what we can have. Anyway, rockfall sort of drives everything. And this just shows, the sort of a cross-section of the glacier. There's rock on top, but there's a bunch of rock within it too, because as ice melts, all the rock on top gets covered by new snow in the upper part. And anyway, it ends up in the middle of the glacier. And at the bottom of the glacier, the glacier is moving and sliding sometimes, and rocks are grinding other rocks, so you get stuff at the bottom too. And the whole thing's moving and dumping it in the river. But there are people there's like 2 or 3 projects now going on to measure how that rock comes off the glacier and into the river. And this is the terminus of, I guess, 2014. This is really unsafe. This was a group from East Carolina University, and I really had no control over them. They're way too close to the terminus, but they were measuring it with a LiDAR thing. And rocks were actually going over their heads. It was very unsafe, so be very careful if you ever go up there. I'll do just one more thing, and then I will call it a stop here. We noticed, remember I was saying how they drilled those melt stakes into the thing? Well, actually it was Stephen Lofgren, who's a lead climbing ranger now. He GPSed them one summer and noticed they really weren't moving. And I just have this map up. This is an old USGS map, but it just shows how much stagnant ice. In 1950, all this was stagnant. I mean, it went down to here. And even in 2009, this part was stagnant. So we had stagnant or non-moving ice at the bottom before. And all our stakes were up in the so-called active ice, but they appeared not to be moving. And the reason that was a concern, besides the fact that you might be losing the glacier, is that stagnant ice is known. Remember, it allows those ice caves to form like you asked. Well, it can also, if water is building up below the glacier doesn't move and have a new crack, a new crevasse, and let it drain out. It can actually, in certain conditions, a lot of water can build up under the glacier and literally float the glacier and then come out as an outburst flood or yokel. And that's a picture of one that happened in 2001. And that's an Icelandic word, I think, meaning big flood. But it's essentially like you have the Nile coming out of your glacier for 5 seconds, and then it goes back to normal. You don't want to be there.
Which river is that on the right?
That, I think, is Tahoma Creek. I'm pretty sure. That was right before I got to the park. I think that's Tahoma Creek. Anyway, if you ever walk around in the glaciers in the summer, and this is on the left is the Emmons, there's literally a river now, a new river running on top of the Emmons, and there's dippers, those birds are on it, it's getting a whole ecosystem, but there's water all over the place. And that can drain to the bottom in things called moulins, which are really cool. They draw people in, and they're so scary looking because they go to the bottom of the glacier. And I had to always pull the interns back from it. I don't know why I put this. Anyway, interns, if you ever have them, they'll do anything if the camera's on them. This is artesian flow where the water's under pressure, and it's very dirty water because you know how the glacier water looks like. Anyway, they were posing. Okay, back to the main idea is that the fear is that the lower Nisqually is going stagnant or not moving. And the reason that's important is the only time where we are, we're right across the river, the only time that actually flooded was the 1950s when they had an outburst flood from the Nisqually. And that's when they put that really big bridge in. If you're wondering why that bridge is so high, it's because they had a huge flood. It only lasted, like minutes, but it flooded all of Longmire. So we used traditional surveying where Scott set up a total station below Glacier Vista. And then, I have to backtrack. This was a volunteer project. For 2 years we had a ton of volunteers going out on the lower Nisqually for twice a week all summer, and they were great. Couldn't have done it without them. And what we would do is we'd identify rocks and mark them and carefully measure where they are twice a week to see how fast they're moving. And we had some challenges. We were actually getting a kinematic wave, so the surface was all broken up. It would take us forever to get places. And we had problems of our measured rocks would fall in the crevasses. But that's another safety note. But we were able to tabulate the data 2 seasons. And what I'd like you to take is that the ice up, this is the middle of the glacier, and this is the bottom. In the middle of the glacier, it's normal. It's moving a couple of feet a day. So every day, the ice is moving a couple of feet. We actually measured some places up here moving 8 feet a day. That's the fastest we saw any ice moving. But the bottom of the glacier, the ice was going nowhere. It just wasn't moving. So middle of glacier moving, bottom of the glacier not moving. And then we took the difference of the 2 years, and the only thing you have to notice is that between the 2 years, the upper part of the glacier started moving even faster, and the lower part just stayed not moving at all. So the upper part's moving, it's allowing all that melted water to go flowing down and get trapped in the lower part. So we're thinking the lower part has a higher hazard for outburst floods. So, and actually, these outburst floods can be huge or they can just be small. There was, in 1974, this guy Stephen Hodge, who was a USGS glaciologist, measured an outburst flood that was like 1.5 meters, like 4 feet or something. And that's just a stream gauge. It just shows the river going up 4 feet and then dropping. The exact, sort of almost exact same looking thing happened in black here on October 2012. And the interesting thing is, this is Scott Beeson's data. The red is water temperature. And right when we got this spike, 4 feet of water just coming down the Nisqually for no reason, the water temperature dropped, which sort of shows it was glacial origin. So we really think it was an outburst flood. And when they looked at the river, they saw these erosion marks. You could actually tell something kind of big had gone down. So we haven't had a huge outburst flood, but we've had one that's big enough that we were able to measure it. And then these usually turn into debris flows, but I think you've all had enough, so I will call it a day here today. Thank you very much. If there's any questions, I'll be happy to take them. Yes.
I was wondering if there's some things that you would like meadow rovers to share with visitors. There's a lot of information you shared with us. I wonder if there's a couple of takeaways that you think would be especially valuable.
Well, I think if they're interested, I know meadow rovers probably don't want to get an argument about climate change with anyone, but if they're interested, I've had people ask me about the glaciers, and they're very interested in the state of the glaciers, and I think that's one that's worth telling. And the ones that they're seeing on the Paradise side, they're all south facing, so because they get so much sun and so much snow, that they're really sensitive to changes, and because things are getting warmer, they're responding even more in terms of the glaciers apparently shrinking more than the other side. The other side are just kind of deflating. So that's a message that the glaciers are in kind of bad shape, and they're reflecting what's happening globally.
People ask why they're so dirty.
That's that rockfall question.
That's what it is.
And because they're melting more, think of it, they're going to be dirtier looking. But there's sort of the silver lining or dark lining that if you get enough rock, actually if you get more than like a 1/4 inch, it actually insulates the top. And if you're on the Sunrise side and they look at all that dirt at the bottom of the Evans, there was I can't remember the exact date, there's a huge rock fall from Little Tahoma. And there was so much rock that came down, it actually, the weight actually caused the glacier to advance. Anyway, that's keeping the Emmons from retreating quickly because there's just a ton of rock there. Also, there's some USGS people who will not sleep in White River Campground because of rock falls.
Oh, I think your date was 1967. I heard that somewhere.
Okay, I think you're right. Yes.
When I look up at the Couch Glacier, it looks like it's just going to tip over onto, this is like that hanging thing that's right up there.
Oh, this is that ice fall?
Is it that ice fall? I always wonder what keeps it from not just.
Well, it is named Camp Hazard under it, but it's named for a person.
Okay.
And it never, they always said, it's not a hazard. Well, it then turned into a hazard, so I guess it is breaking up a bit. So I think there, at least 5 years ago, they were asking people not to camp right there, like they used to. So it's just, well, as it gets warmer, glaciers move more. As it gets warmer in the upper glacier, you actually get more melt, and you get water going to the bottom. And I didn't really get into this, but it moves 2 ways. The ice moves from its own weight to forming. And also, if you get enough water at the bottom, it slides. It helps just lubricate it. So if you get more lubrication higher in the mountain, you're going to get more faster movement, and you'll get ice falls making more noise. Yes?
In terms of the future, do you expect glacial retreat to increase? Because I look at those photos of the Muir snowfield, and I climbed Rainier in 1990. It was totally different then. There's so much less snow and ice now than there was then. I mean, are there predictions about, all that completely melting in some period of time? Or
Climbing rangers, at least anecdotally, have started figuring out routes without glaciers. And if you took that work, I started back that glacier volume thing near the beginning. Well, we made maps. You could easily just take the glaciers off the mountain and see what it looks like without it, because we mapped the bottom and the top of the glaciers. You could technically. So people have started thinking about that. But remember how I said you can see, it's easy to see glaciers from Seattle? Rainier would not look anywhere near as iconic if it weren't white. It would look kind of just this black blob out there, which won't happen. It's always going to be white at the top. But yeah, and to short answer your question, people have started thinking about it. And it's probably more hazardous, more harmful. And you had a question.
Did I hear correctly that the White River is 8 or 10 feet higher than the 410 in some places?
Some places, well then 410 it's 16 feet higher. In some places it's not where 410 is, but in the White River Valley, it's up to 20 feet higher.
Where is that?
Well, if you're driving out the Crystal, driving the Crystal exit, on the left, like a mile away, you'll see there's a wall. That's that area I showed. They built the wall since. Right there is a place. If you just went right angles to the road, just go below or above it, just walk in till you find the White River, and you notice you're walking uphill the whole way, and you'll notice all this sediment and some of the old growth trees, these beautiful old growth trees are dying from water flowing over. So that's where, and the carbon is all over the place. It's way higher than you can walk the Carbon Trail now to see the river above you.
Does the red snow algae that visitors ask about play any role in this story?
Does it what now about it?
The watermelon snow
Right.
that visitors will ask about, is that play any role here, or is that
Not that I
something
know,
else?
but I'm wondering if I don't know what conditions it likes. It may get more of it or less as things warm. I mean, I don't know the answer. That'd be a good question to ask, because you're right. I get questions about that all the time.
Okay.
I tell them not to eat it.
Yeah.
Yes.
Additionally, the Clark literature says there's 25 active glaciers main glaciers on the mountain. You showed us that 8 have disappeared in your lifetime. So what would be the accuracy right now?
Oh, 25 is that document of Scott Beeson's, which was 2017. There were 25 that were still viable glaciers then. And that's how we decided there's 25. Because that's been a question all the time. Maps sometimes show more. So there are 25, and I would refer to that as sort of the official word.
Okay.
Unless, we can show that one of them's disappeared since then. Which is very possible. I doubt it has, but it's going to be close.
Okay, right.
So 25 is a safe number, yes.
If we are lucky and smart, and we're able to get control over the fossil fuels burning quicker than we anticipate, will they start to grow again, the glaciers?
I think they will, but I'm not totally an expert on the actual climate science stuff. But it seems that we've already created problems that go a couple decades. So they're really talking about what happens now. Do we really go over like an edge in a couple decades? So things don't look good for the next couple decades, no matter what we do. So it's going to get worse. Now, you have natural variation too. So even though the tide is out, you still get like the waves coming in. So you could have some good years. Like we actually, until we had that heat dome event, had more snow than normal, for example. So that looked good for a while, and then suddenly it didn't look good. But I think there won't be any, during my lifetime anyway, there won't be any real increases in the size of the glaciers.
Maybe 50 years from now?
If we really crank down, yes, because I think they're only talking about a couple decades. Our die is sort of cast for that. Okay. Well, thank you very much.
Great. Thank you, Paul.